Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to be just a conceptual introductory video about the differences between DC voltage and AC voltage. So let's start with DC voltage. So DC stands for direct current, and what that physically means is that the current doesn't change direction. So DC voltage sources, the most common here, are batteries. So here's a picture of maybe, like a 1.5 cell battery, and here's a picture of a 9 volt battery, and here's a 12 volt here that we're going to talk about running this this lamp. All right, so batteries provide DC voltage sources. Now, if we look at this example, in this case, this 12 volt battery here running this this bulb here. This is the red or positive terminal of the battery. And what it does is it attracts electrons. So the electron flow in the circuit, if you will, is this way. Now, if you've seen my other videos or anybody else's about current, current is typically defined by positive charge carriers. So even though we're talking about electrons in the direction shown, the current direction associated with this, assuming positive charge carriers, is actually this way. If we were to plot voltage against time, the voltage output of the battery here, it might look something like this, basically. Now, it probably will, I'm not taking into account the fact that the battery will eventually drain and the voltage will fall off. At least for a short time, the voltage will be relatively constant. So this is what it'll look like. And because the voltage isn't changing direction, neither is the current. So the current in that example will always be counterclockwise until the battery goes dead. So that's an example of a DC voltage source. Now, let's chat about AC voltage. So the AC stands for alternating current, right? And the word alternating is implying some sort of reversal. And it has to do with the voltage and current directions, which constantly are changing. So here's a picture of an outlet. So from the simplest step here, as far as most people watching this, this would be the most common source that you would find for AC voltage. All of the outlets in your home are giving you access to an AC voltage source. Now, where does that come from? It comes from electric generators. And I'm just going to make other videos on generators. So this is not the voltage source, if you will, but it is the probably first contact you would have with that voltage source, I guess, if you were living at home, i.e., you would plug something in. So when you plug in a lamp or something, effectively what it does, there's multiple wires within this. And I'm just going to kind of connect them to our bulb here. And I'm going to connect them like so. Boom. And here's the thing about these outlets. This one right there, that small one there, that's the one that's considered live. It's the one that basically carries the voltage in it, I'll just say for now. This is the return. It's electrically neutral. You can't run anything off of that directly. This one is a safety feature. That's hooked to the ground. And when I say ground, I'm talking literally the earth. Now, the purpose of this one is not within this video here. I'll make other videos about what that thing does. So basically, when we plug our lamp in with some sort of cord, we are connecting this, where the voltage is varying, to this, which, if you follow it far enough, goes all the way back to the source, which in the overwhelming majority of the cases will be the power company. So it's all about this one, the short one right here. So when you are working with AC power, or let me back up, in the United States, in the power grid in the US, the voltage that comes out of this, half the time it's at you, kind of like this way in the picture, half the time it's away. And if you were to make a voltage graph, it would look something like this. Oops, I could do a better job than that. Okay. So this is what is referred to as a sine wave, and of course this would just keep going and going and going. Now, in the United States, the peak of this curve is approximately 170 volts. Down here, that means on this graph we're getting down to minus 170 volts. Now, first of all, there's really no difference between them, right? Or let me restate that. The difference is the direction. So if we get back to this outlet here, that conductor right there, half the time the charge is being pushed at you, if you will, half the time away. So if we call the at you's positive, that would be here, here, and here. Then the other direction would be here, here, and so forth. Right? Now, this waveform is referred to as a sine wave. It's a sinusoidal function. I'm just going to say this. It's equal to sine of some sort of angular velocity times time. It has a peak of 170 volts. So the function that actually describes this looks like this. The intent of this video is to not to talk about the mathematics of it, though. I'll save that for other videos. The intent here is just to be kind of a conceptual video. Now, the 170, most of you looking at this are probably thinking, I've never heard of that, the 170. Usually these outlets are classified as either 110 or 120 volts. Okay. Well, here's what the 120 is. It's an average voltage. See, the peak, the 170, is the highest point. But you know, if you look at as time goes on, the voltage is only 170, like here, 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 only at the peaks of these curves. So the overwhelming majority of the time, the voltage is much less than that. So what we always care about is power transfer. And this voltage right here, 120 volts, that's called your RMS voltage. Oops. Which stands for root mean square. I don't feel like writing that all out. And your RMS voltage, what it is, right, here's how it's defined. It's the DC voltage, I'll just put VDC, that has the same power output as this voltage source. And the way you go back and forth between your RMS voltage and your peak voltage is this. Your RMS voltage is equal to your peak voltage, or I like to say your max voltage, divided by square root of 2. If you take the 170 volts, divide by the square root of 2, you're going to get something right around 120, probably 118, something like that. So that's what the 120 is. It's an average voltage, averaged by power generation. Another very important thing about AC circuits is the frequency. So in the United States, the frequency of the power grid is 60 hertz. And on our graph, that means this, that the distance between, any 2 points on this wave, so I'm going to go here to here in green, is 1/60th of a second. I'll just do this, 1/60 seconds. Now, something to notice here is, in just that single wave, you notice there's actually 2 peaks. A light bulb doesn't care which way the voltage is going. So if you were to look at this bulb right here very, very carefully at high speed with a high-speed film, what you would see is, if you slowed it down, you would see the bulb bright 2 times in a 60th of a second time frame. So the bulb actually brightens up 120 times per second. Another consequence here, mathematically, because we're at 60 hertz, then the input voltage, or our voltage, the AC voltage in the US power grid mathematically works out to this, 170 volts times the sine of 120 pi times T, because what's called your angular frequency is 2 pi times this frequency. So let me just kind of go over this big ticket things again. DC voltage stands for direct current. Here's an example of a DC voltage running a battery, or running a light bulb. And the big deal is that the voltage and the current, they stay constant in direction. So a voltage graph would look basically something like this. Whereas with AC voltage, that stands for alternating. Right? That comes from electrical power generation. And where you tie into that, if you will, is at home, right, with these electrical outlets. And here, rather than a constant voltage, you get a voltage that varies like this. Half the time it's in one direction, half the time it's in another. And it varies, or I should say the length of one wave is a 60th of a second, or another way to say that is the frequency is 60 hertz. And again, the peak, 170 volts. Now, When you work problems with AC voltage, you always want to use what are called the RMS values. That's a little hard to read there. And your RMS voltage is equal to your peak voltage divided by √2. Any problems that you're working about the US power grid, you will typically be using 120 volts for your RMS voltage. Now, some good news about like working problems. Well, it kind of depends on how complicated the problem is. But for problems that only involve resistors, toasters, light bulbs, things like this, you typically will just be applying Ohm's law, like voltage equals current times resistance. And you're going to use RMS voltages here, and you'll be getting out what are called RMS currents. And then power calculations are the same, right? Power can be calculated by current times voltage, or I squared times R. Just make sure you use RMS values for currents and voltages. So again, this is meant to be just kind of an introductory video about AC voltage and how it differs from DC. I hope that this has done a good job for you. Have a great day.